Okay, morning. So let's continue on the Fourier series. Okay. Before we talk about the Fourier series, just to reconfirm, our final exam is not cumulative. Okay, but as I have said, you do need to know the knowledge before the midterms in order to do all the everything. Okay, after the midterms. So for 246, so we'll go in detail later. For 246, we'll retest the convolution. That's basically the only part we're going to retest before the midterm. So we're not going to have a question dedicated to system properties, to first order differential equation solving using the integrating factor methods, right? But we do pick up the first order differential equation that we left over from after midterm. For example, Bernoulli equation, homogeneous equation. Okay, yeah. So same thing for 248. Okay, so the a lot of the partial differential equation, vector idea, dot product, cross product, lines, planes. So those things that you will need them in order to solve the questions for the final. Okay, yeah. As a matter of fact, I think that I emphasized it quite a bit. The last 4 lectures, basically including the 2 lectures of this week, 248. Okay, I know a lot of people are not coming, but I think for those of you who are coming, I can emphasize you. A lot of questions are coming from the last 4 lectures, basically of 248. Okay, so as I said, because the last 4 lectures is basically the application of everything that we have learned, okay, in 248. So, for example, the last 2 lectures that we're going to have with the 428 last 2 lecture, I can guarantee you at least there are 2 or 3 questions out of the last 2 lectures. Okay, yeah, maybe even maybe 3 questions. So make sure you hold on to the last second of this of the course. Okay. Okay. So there's no slack here. Okay, so Fourier series. Okay. Fourier series is basically, as we were talking about here, we were talking about basically for a periodic function. Okay. What we do is we're trying to decompose this periodic function into a sum of harmonic oscillations. Okay. So first of all, what's the harmonic oscillation? Harmonic oscillation basically, okay, one signal is oscillating at 2 Hertz, the other signal is oscillating at 4 Hertz. So it's a scale multiple of the previous frequency. Then this is basically called a harmonic oscillation here. All right, yeah. And what that means is, right? Basically, let's see. Here's the definition. Let's say consider a periodic function or signal, okay, g of t. Okay, so by periodic, basically it means let's say this is a periodic signal with a period of capital T. Okay. So by periodic basically means this g of t equal this g of t plus capital T. Okay, yeah. So actually there's one little thing I want to mention is g of t equal to g plus t capital T. You should also know that this is also equal to g of t plus 2t or t plus 3t or equal to g of t plus, let's say, nt. Okay, that's a property of a periodic function. Now, this t at here basically what we call the fundamental period, right? Yeah. So, if this is a periodic function, then this g of t, okay, will equal to a naught, well, plus a summation at here, okay, n from negative infinite to positive infinite, okay, an cosine n omega naught t plus bn sine n omega naught t. Okay, so this is the so-called summation of this harmonic oscillations here. So you can see this cosine and sine, there's basically oscillations. Okay, why is it harmonic? Because you see here, this is n omega naught. So basically the difference between each one of sine and cosine, they're just multiples of frequency at here, right? Yeah. So the omega naught at here is 2 pi over this t. Okay, 2 pi over t. So t is the period, omega naught is the frequency. Right, the frequency. Okay. Yeah. Okay. So now the question is, okay, what would be this the value of a naught, an, and bn, given? Actually, sorry, this is not negative. This is from 0. This is from 1. Sorry, this is from 1 here. What would be this? What would be this coefficient an, bn, and a naught for a given harmonic, or a given periodic function g of t, right? Yeah. So I'm gonna give you the formula here, and so let's see if I need to prove or not. So maybe just prove one of them. So the an, okay, bn, first four, they're called Fourier coefficient. Coefficient. And this a naught at here, okay, this a naught value, this is so-called DC component. Okay, this is so-called DC component. And the rest of them, basically the second term, that's anything involving the sine, cosine, those are called AC components. Maybe I'll just write it here. So this term here is called AC component. So including the summation, okay, every one of the sine, cosine here. Okay. So you'll see why it's called AC component, the DC components. Okay. Yeah, but let me just give you the formula here now. Let's see, what's the A naught, what's an, bn here, right? Yeah. So let's say I'm trying to find a naught, okay, and an and bn. So I'll show you how to find a naught, okay, and then you have a similar idea of finding an and bn. So let's say I'm gonna find a naught. So what we do is we do this. We're gonna to find a naught, right? So we're gonna integrate. Okay, here is the g of t equal to this here, right? So we're going to integrate both sides of this equation, okay, from 0 to t. Basically, integrate both sides over one period. Okay, so integrate this guy over one period, and the other side the same thing. Integrate both sides over one period. So now there are two terms. So this is a naught at here and dt, and 0 to t, and summation of everything here. Okay, now what happens is there's a very neat property at here. Okay, very neat property. So here's this property here. So there is a property. Basically, there's a one set of function. Okay, so just on side notes. One, okay, cosine. Let's say cosine omega naught t, sine omega naught t, cosine 2 omega naught t, sine 2 omega naught t, and up to cosine, let's see, n omega naught t, and sine omega naught t. Okay, So here's a very special set of functions here. So those functions, first of all, okay, those functions here, okay, they're linear independent. Second of all, this is the integral of multiplication of each one of the functions within this set is so-called orthogonal here. So what it means is basically when you integrate, for example, when I integrate, okay, these two, multiplication of these two here, okay, integrate over one period, and the value is 0. Okay, value is 0. So basically means this 1 and the cosine omega naught t, this is called the two here, they're called orthogonal. Okay, so essentially the idea is when you're integrating, let's say, from a to b, and the function of f of t, g of t, dt, if these two are 0, and this f of t and the g of t, right, is called, okay, orthogonal. Okay, it's called orthogonal here. So that's just on the side of notes of the little new thing here. Okay. Yeah. So similarly, if you use your 1 multiplied by sine, actually it's very easy to verify. Okay, very easy to verify. So you can integrate it. Omega naught here is 2 pi over t. Okay, omega naught is 2 pi over t. So you can just what's the integral of cosine omega naught t is 1 over omega naught sine omega naught t, right? And then you plug in the limits here. You'll see that they're 0. Okay, yeah. So similarly, the sine omega naught t dt will also be 0 here. Okay. And of course, if you put an n here, it's going to be 0 too. Okay, yeah. So now come back to what we just did here. Integral of this whole thing, right? The second term here. So what are we integrating? We're integrating 0 to t, this term, that term, right? Yeah. So the summation sign here can be pulled to the front, and then integrate what's inside the bracket here, right? So basically, the whole second term here, according to what we just said here, is going to be 0. 0. So this whole term here, it is 0. Okay. So that basically left with the first here. So that, you see, the first one here, that's easy now. So that's basically what we have here is 0 to t, g of t dt, and this integral is what? A naught multiplied by t, right? A naught multiplied by t. Okay. So we're looking for the value of a naught. So then this a naught equal to 1 over t, 0 to t, g of t dt, right? So that's a naught. Okay? Yeah. So g of t is a periodic function that's given, right? So how periodic? Maybe it's a sine, or maybe it's a cosine even, right? Or maybe it's a box repeating itself at a certain frequency. So that's a periodic function. Okay. So then you use the given periodic function, you integrate the periodic function just over one period of that, and then divided by t. That's the a naught, which is what we call the the DC component, right? The DC component. So how about a and b n? You can use the similar approach. Okay. So to find, I'm not going to write the detail now. To find a and b n, so what you do is, right? You multiply. Let's say find an a n first. Okay. You multiply. Okay, cosine. You multiply this cosine n omega naught t. Okay, to both sides. Okay, to both sides. So you multiply this. Here's this g of t equal to this, right? So you multiply this cosine omega n t, omega n naught t over here, cosine omega naught multiplied to both sides here. Okay. Then you integrate both sides to over one period. Okay, integrate over one period, and and then we're going to make use the similar properties that we said, the orthogonal property of this set of the sine cosine here. Okay, and we are able to do some simplifications, and we'll be able to find a n here. Okay, so take a look at the lecture notes regarding how this process is being carried out. Okay, so I'm just going to skip myself a couple of steps here. Okay, but all we're going to find is, okay, a n, okay, and then say integrate. Okay. So that's the process. So we're going to find a n equal to 2 over t, 0 to t, g of t okay, cosine n omega naught t dt. Okay, and the Bn is 2 over capital T g of t sine n omega naught t dt. Okay, so that's A and Bn. Okay. All right. So one of the things I think, if you look at the three formulas, okay, for the A naught, A and Bn, okay, they're not too bad. They're just basically involving sine, cosine, and the original periodic function, right? Yeah. And what you need to calculate or evaluate the integral is you need to know what the period of the function is. So how do I tell what the period is? You look at the graph, right? Look at the graph. How at what time what period is repeating itself. That's the period. And you need to figure out this omega naught, and so that's based on the value of the period, 2 pi over t. Okay. Then you integrate. Okay, keep the n as a general number here. Do the integral. Okay. Yeah. So then that's going to be your A and Bn. All right. Yeah. And what's the n value? The n value is right from 1 to infinite. Okay. This is not negative. This is 1 here. Okay. So from 1 to infinite. So you can use 1 up to any number you want. Okay. Yeah. So sometimes you don't need to list everything. You know, sometimes we say, what is the g of 4t? So basically, you're talking about I'm going to use 4 terms, right, to approximate the g of t. Okay. So in this case here, you're taking your capital N equal to 4. So from n equal to 1, 2, 3, 4, right? So that's basically what you do to approximate that g of t, right? Yeah. So number of terms, basically. Okay, good. So now let's take a look at an application, an example here, okay, in terms of this Fourier series here. But before we move on, okay, so let's take a second look at this formula here, okay? Let's take a second look at this formula. Okay, so this is g of t, and now we are decomposing it into sine and cosine additions. Okay? We know that the g of t has a base frequency omega naught. Okay, that's the base frequency, right? So g of t has this so-called fundamental frequency omega naught, okay, equal to this. Okay, this. Now, let's say when we decompose that, okay, into this one here, particularly the second part here. Okay? So when n equal to 1, right? When n equal to 1, what this cosine is what omega naught, this sine omega naught. That's basically the fundamental frequency, right? And then when n equal to 2, this is 2, 3. When n equals 3, 3, 3. So what happens is it's not a random. Basically, it's not random of a summation of this harmonic. It's always a multiple, right? It's always a multiple of the base frequency. Okay, so you're decomposing essentially the original periodic function, which has a fundamental frequency omega naught, using a what? Using a linear combination of multiples of this fundamental frequency oscillations, right? So 2 omega naught, 3 omega naught, 4 omega naught, 5 omega naught. Okay, not 1.5 omega naught, not 1.2 omega naught. Okay, yeah. So that's the idea here. Okay. Okay, let's take an example. So let's use a periodic function, which is this one here for illustration here. Okay. Okay, so here's a box repeating itself. Okay, so the box is defined as this. Okay, so this is the box set here. Okay, here's the box. So how does it repeat itself? Right now, it's repeating itself like this. Okay. So let's call it g of t here. Yeah. Okay. Yeah. So once you have this diagram now, right, and without telling you anything else, you should be able to carry out this Fourier series expansion just based on this this diagram now, right? Yeah. So first of all, you can tell this is a periodic function. And then second of all, okay, what's the period of this function? 2. That's right. It's because it's repeating itself right here, right? So this t equal to 2. Okay. Yeah. For one of the example that I did, okay, in one of the assignments, let's say just not this example, just aside here. Let's say maybe I have, okay, let's say maybe I have a sawtooth function like this, right? Okay, and if this is 1, if this is a 2, and here, let's say, right? Okay, this is 2. Okay. So what will be this periodic function? T will be 2, 1, right? Because it's repeating itself like this, right? But how about now? I said how about then the next question is, what is the function g of t, right? What's basically, how do you express the g of t? Let's say for the first one here. Okay, for the first one here, okay, g of t. Okay. In this particular case, between 0 and 1, the value is 1, right? It's 1. So when t is between 0 and 1, is 1. And when t is between 1 and 0, it's between 1 and 2, it's 0. Okay? And then you should also see that the g of t equal to g of t plus 2. Okay? So that basically tells you this is a periodic function like this, right? Yeah. How about the second one here? What will be this g of t? Okay. What will be the g of t at here? Right, that's right, 2t. And that's t between 0 and 1, right? And then the period is t. Okay. So that's basically how you can summarize the given graph here, because you need information. Okay, so you may not be able to. So the question may not tell you exactly what this function is. Just give a graph, right? You can summarize this given information based on here. Okay? But I'm going to use this example here. Okay, use this graph here for example. Okay, so let's say I'm going to decompose that into a sum of sine and cosines, okay, for this guy. So before we move ahead, so let's take a look at this this graph here. Now this kind of graph is typically what we call it's oscillating, right? It's oscillating, and it's always oscillating at a certain kind of average value, right? So for this kind of thing, generally we call it an AC signal. So AC signal not necessarily is always a sine or cosine, right? So when you have an AC signal, and you always have average, and this average is what we call the DC component. So for this particular one, it's very easy. Look at this one here. What do you think its average is? 1/2, right? 1/2. So the DC component here is going to be 1/2. So according to what I just said over there, and this A0 value is supposed to give you 1/2, right? 1/2 here, okay? But however, okay, I do need to calculate, okay? So let's verify this this idea here. Okay? So A0 equal to 1 over t, 0 to t, okay, g of t dt. The capital T here is 2, so that's 1 over 2. Okay, 0 to 2, okay, g of t dt. Okay. Now you go back to your definition of a g of t here. You look at this g of t, 0 to 2. So do you need to integrate all the way from 0 to 2? No, you actually only need to what? Integrate from 0 to 1, right? Because 0 over here. So that means this integral here is just 0 to 1. And between 0 to 1, the value of g of t is 1. Okay? Yeah. So overall, this is 1 over 2. See, that's exactly what we are expecting to be. Okay. Any idea? Any answer? Any questions? Yeah. All good? Yeah. Okay, so now let's take a look at the AN and the BN here. Okay? an, according to the formula, is 2 over capital T, 0 to t, okay, g of t cosine n, okay, omega naught t. Okay. That's an. That's an. So let's plug in the known numbers. T is 2. Okay. If t is 2, okay, then omega naught will be what? Pi. That's right. So let me write down this one here. So t is 2, omega naught is 2 pi over t is pi. So that's cosine n pi t dt. Alright, replace the t with the 2 at here too. Okay, yeah. Okay, so then you do the same thing. So you don't integrate over 0 to 2 all the time. You only integrate from 0 to 1 because only exists between 0 to 1. So this 2 over 2 is 1, so this is 0 to 1. Between 0 to 1, the g of t is 1, so this is basically cosine n pi t dt. Okay? Now this is a cosine n pi t dt, and this is integrating from 0 to 1 over one period. So as a matter of fact, so if you're confident, okay, so here's the assumption, you're confident, according to what I said here. When you have this set of this one here, right? This 1 and cosine n omega naught t, they are orthogonal. So when you're integrating, okay, over one period, then you're supposed to get 0, right? Yeah. So for this particular one here, so you're supposed to get a 0 if you're confident enough. Okay. If you're not confident enough, so here's what I will do next. Okay. So we'll just carry this integer out. Okay. So this is cosine n pi t. So the value of that is 1 over n pi, and sine n pi t, and go from 0 to 1, right? 0 to 1. So you plug in 1 into it and 0 into it, so that's 1 over n pi sine n pi minus sine 0. Okay. Sine 0 is always 0. Sine n pi, right? Remember the n is from 1 to infinite, so n is an integer number, 1 to infinite. So sine pi, sine 2 pi, sine 3 pi is always 0. Okay, it's always 0. Right? So what's the sign? Sign is, this is sine, right? This is a pi, this is 2 pi, so 3 pi, right? Yeah. So this whole thing basically is 0 here. Okay? Yeah. Okay, so any questions? So good? Right. So here's what I mean here. Okay, so if you're confident in terms of using some of the properties, okay, sometimes if you're running out of time, you want to take a guess, so that's okay. But okay, you can always calculate, okay, in order to make sure. All right, so let's calculate the Bn net here. Okay, Bn. So Bn, okay, plugging these numbers, it's 2 over 2, 1, and 0 to 2. Okay, g of t, same thing, sine n pi t dt. And we're integrating just over 0 to 1, okay, sine n pi t dt. Okay, so that's Bn here. Okay, that's Bn. So the value of this one here is 1 over n pi, okay, and then negative cosine n pi t, 0 to 1. So now let's plug in the numbers. Okay, plug in 1 over here, 0 over here, and what do we get? We get 1 over n pi, so negative cosine n pi first, plus cosine 0. Okay. Right, so 0 negative become positive. Okay. Cosine 0 equal to, what is cosine equal? Cosine 0 equal to what? 1. So the next thing is cosine n pi, right? Cosine n pi. Okay, so let's take a look at the cosine here. this is cosine here. Okay, so what's this one here? This is pi over 2. This is pi, right? This is 2 pi. This is 3 pi, like this, right? Yeah. Yeah. So n is 1, 2, 3, like this. Okay. So when you plug n equal to 1 here, cosine pi is -1. When you plug n equal to 2 at here, you got 1. When you plug 3 over here, and that term becomes -1 again, right? So basically, cosine n pi, you look at this curve here, that equal to, it's oscillating -1, 1, 1, and then -1, 1, -1, -1, like this, right? So how does it oscillating? It's oscillating like this, right? -1 to the power of n. Excuse me. Okay. So when n equal to 1, it's -1. When equal to 2, 2 pi, that's 1. See, that basically match this in here. Okay. Yeah. Okay. So that's the cosine n pi. Okay. So then overall, right? This term in here, over this term. So what you can summarize is, so when n is an even number, so when n is 2, 4, 6, and this 1 minus 1 is 0. So basically it's 0 when n is even, right? Yeah. And when n is odd, okay, when n is odd, this is become 1 plus 1, so which is 2. So that's basically 2 over n pi. Does that make sense? Yeah. So that's Bn value, right? That's Bn. Okay. Yeah. So now I can summarize. I'll summarize saying, okay, how would I express, or how would I approximate my original periodic function, this g of t, okay, equal to a naught. A naught we calculate is 1/2. Okay, so it's 1/2. Okay. And plus, okay, the summation of the a n b n thing, but because a n is 0, so we only have b n there, and b n exists only when n is odd number, right? Means odd number. So this sum here, you can see that this is n starting for is 1 and n is odd. Okay, okay, you can see n is 1 and n is odd toward infinite, and then here's 2 over n pi, okay, multiplied by sine n pi t, right? So that's how you approximate this c of t. If you write a few terms out, it's 1/2. Okay, so let's write a few terms. Plugging n equal to 1 here, okay, which is this, and plugging n equal to 2. No, plugging n equal to 3 now, right? Because n is odd. So plugging n equal to 3, so that's 2 over 3 pi sine 3 pi t. And plugging a little more here. Okay, so you can keep going. Okay. Yeah, so that's g of t. Okay. So g of t can be approximated, okay, using this thing here. Yeah. No. One period. Actually, yeah, g of t was just 1 period t. Yeah, t equal to 2. Yeah. So actually, you just actually have a very good question here. What you probably were saying is, when you look at sine pi t, the period is what? 2, right? 2. When you look at sine 3 pi t, the period is 2 pi over 3 pi, which is 2 over 3, right? And when you look at this, so basically this period is different from this period here. This is actually a little faster, right? So this basically frequency is faster. So there is this little theorem basically. When you have this one period is here and the other one is basically a multiple of the frequency of the first one here, then the overall frequency is still the same frequency as this one here. Okay. So what I'm going to show you this. Let's take a graph of this thing here. Okay, let's take a graph of this. I'll show you this. So essentially, the question is, you're trying to approximate the original periodic function using a number of terms of the sums, sine, and cosine here, right? Yeah. If you use infinite, you have basically absolutely exactly the same approximation, okay? But if I use a limited number here, then I would be able to observe some difference, right? So this is the little graph right here, okay? So you see this black one here is the original g of t. Okay, original g of t. Now, if I just use one term, basically if I just let n equal to 1, so let's say here, right? If I just use let n equal to 1, what do I get? I just have these two terms here, right? These two terms. Then when I graph this out, that's the sign here, right? That's the sign, okay? Yeah. But if I use 2, n equal to 2, so let's see, is that next one is 2? Yeah, if 2, then I have this one here. This is n equal to 1, this is n equal to 2, okay? Yeah, and this is when n equal to 3. Okay? Well, I mean not equal to 3. This is, let's just say this is 2 terms, right? Yeah, this is 2 terms, or n equal to 3 here, right? Equal to 3 here. Yeah. This is how many terms? Actually, up to n equal to 5 now, right? This is up to n equal to 5. Okay. Yeah. So you can see now, as you use more terms, the approximation, the green one is the one with the n equal. Actually, say n equal to 5. Actually, so you have a better approximations here, right? A better approximation. Okay. Is that clear? Yeah. The second observation is this. Second observation. Now, you see, basically I can conclude that my original periodic function contains a base frequency of pi, contains a base frequency 3 pi, not base frequency, contains a multiple of that, 3 pi, contains a multiple of that, 5 pi. Alright? At the same time, you see the coefficients here, right? The coefficients. The coefficients basically tells you what? It's how much contribution from that frequency, right? Say this 2 over pi, 2 or 3 pi, 2 or 5 pi. Guess what? Which one is bigger? This one here, right? So as n is approaching to a larger number, and this coefficient is basically approaching to 0, right? 0 here. So this coefficient that here essentially tells you the contribution of that corresponding frequency to the overall, okay, approximation. Okay, yeah. So this is essentially an idea of this. You're given a periodic function, then the question is how many frequencies, okay, how many frequencies of sine and cosines are inside this periodic function, right? Or maybe another question is, giving a signal, periodic signal, how many frequencies inside there? Does it have a 2 hertz, 4 hertz, or 3 hertz, right? Or 5 hertz, 6 hertz? And at the same time, how much of this energy associated with each one of the frequency? Okay, is it high or is it low? Right? Can it be neglected or can it not be neglected? Okay. So when I'm talking, here's a signal, right? Here's a signal. Okay. Then the natural question is, what's the pitch of this talking here? Is it 20 hertz or is it 30 hertz? Maybe it contains everything, right? Maybe it contains a very sharp pitch of 1,000 hertz that you just can't hear it, right? And because why? Because the coefficient associated with that is very small. Okay? Yeah. So the Fourier series ultimately give us an idea, okay, of how many frequencies inside this periodic function, and what's this amplitude associated with that frequency. Okay? That's basically ultimately what the Fourier series is telling us here, right? Yeah. I have a little maybe just talk about it here. Okay. So let's say a lot of you guys probably play piano or some other instruments here, right? Yeah. So when you play piano instrument, then you have this one octave, let's say, right? Starting with C note and then going up one octave, okay? And between this one octave, there's separated into 12 notes or 12 halves, as we call it, right? Yeah. At each note, okay, let's say C, C sharp, all of these things here. You know, by the way, actually, I don't play anything. So there's associated frequency for each one of them. Okay. Yeah. For example, C, the major C there, okay, is 110 hertz. Whatever. Actually. Okay, let's take it right here. Okay. So now the question here is, okay, if I play a song, right? You know, let's say you have a notes, maybe two notes played together, right? And what sound does it make? Right? Now, this whole thing can be explained very easily using the Fourier series expansion here, right? Yeah. So let's say I have, for example, let's say the base frequency is 262 hertz. Okay, then this is the base frequency. 260 hertz. One second here. Sorry, actually, C note is 262 hertz. What's the 110 hertz again? Only note A in every octave has an integer frequency. Oh, I see. This is a note A frequency, right? Note A. Okay. So this is a note C frequency. Okay. You see the note A, that's an integer number here. As a matter of fact, this is not exactly 262. This is a 262 point something. Okay, yeah. Okay, so if you're playing a frequency of a C note, 262, and then if you have a Fourier series expansion, for example, for a periodic function g of t equal to this, right? So you basically, this is a combination of two things here. So then, if omega naught is the base frequency of the C note, then you have another 3 multiple of this base frequency. So then, overall, what you're hearing is you're hearing, okay, this middle C note plus the 3 times of that. Okay, yeah. So Fourier series, okay, there is actually, take a look at one of the website here, okay, there is a very good Java application you can play around, okay, just kind of manipulate the frequencies, okay, and then you'll see the different kind of sound out of these manipulations, okay. Okay, so we have still a little bit of time in here, okay, so let's take a look at the next example here, okay, just quick examples. Alright, so this is a periodic function right here, okay? This is a periodic function. So for this periodic function, let's say I'm trying to find the Fourier series expansion for this periodic function. So let's make use of some of our knowledge that we learned here to simplify the situation, okay? Simplify the situation here. So number one, okay, A naught. Remember A naught? A naught is called the DC frequency, DC component. So for this particular one here, the A naught must be 0, okay? Because the DC is component 0, okay? So if you want to verify that, you can use the formula to verify this very easily. Then AN is 2 over T naught. Period is T naught, right? So it's repeating itself. Okay? And 0 to T naught, okay, G of T. cosine n omega naught t dt. Okay. So that's an here. So in order to calculate the an, I'll show you two different approach. Okay, two different approach. Number one, okay, is the traditional approach. So if I calculate an, so I'm going to integrate from here to t naught, right? So if you look at this this variation of the g of t, it's 1 between 0 and t naught over 2, a -1 between this to this. So basically, what you need to do is you separate this integral into two parts. Okay, so 1 is 0 to t naught over 2, and this is 1. So cosine omega n naught t plus t naught over 2 to t naught, and negative, this is negative minus here, and cosine n omega naught t dt. Right? So that's how you're going to carry out this a naught here. Then this is the basically sine, cosine, and then you plug in the limits to calculate the a naught, right? The an here, okay? The an. So you'll see that it's actually going to be 0. Okay, going to be 0. Okay, that's a traditional approach calculating these integrals here. And there's also a shortcut here using some properties. Okay, so this is another new thing here. The shortcut is basically dealing with a function called even function and odd function. So f of t equal to f of negative t. This is called even function. And f of t equal to negative f of negative t, okay, or f of t plus f of negative t equal to 0. This is called an odd function. Okay, called an odd function. So now let's take a look at this function g of t at here. So what does it mean here? Basically, this f of negative means it's reflecting about its y-axis, right? Mirror itself. Then negative basically then you do another flip around this horizontal axis. So if you do this one here, reflect and reflect. So this g of t basically is so-called. This is what? An odd function here, right? It's odd function. Okay. And the other thing is, an odd multiplied by an even function give you an odd function. This is like logic here. And odd multiplied by an odd will give you an even function. Okay. And the even multiply even is still going to be even function, right? Yeah. And the other thing is, okay, if f of t is even, okay, if f of t is odd, okay, then integral, okay, from any number a about this f of t will be 0. Okay, will be 0. So a couple of the points here, I need to connect all the points in order to prove my shortcut here. Okay, yeah. Actually, my shortcut, I just want to say that this is 0, right? Okay. So that's the odd one here. Does that make sense? I mean, actually, much makes sense. What's the sign, right? Sign is this, right? Sign is this. So if you take this to this, integral area is 0, right? Yeah. And second of all, okay. Second of all, what I'm trying to say, yeah, this integral here. So the formula I give you is 0 to t naught, right? 0 to t naught. Okay. So in Fourier series, okay, your formula actually the an, okay, the 2 over t, 0 to t naught, okay, and blah blah blah, okay, that's actually the same as, okay, negative t naught over 2, negative t, not t naught, negative t over 2 to t over 2. Okay, so if you integrate it over one period, 0 to t is the same thing if you integrate from negative 2t over t over 2 to t over 2, right? Yeah. So now if I combine the couple of points over here, okay, combine a couple of points here. So let's say now, right? Now, what we just said here, g of t, this is what? Odd here, right? And what's cosine? Cosine is always a even. Okay? It's always even. So then this odd by even is a odd. And integrating 0 to t can be changed to negative t. This is not, I use a t naught. You can change that to negative t naught divided by 2 to t naught divided by 2. So overall, you can see this thing here is 0, right? Yeah. But Bn is not 0 though, right? Yeah. Any questions? All good?
In this case, since A naught or AN is equal to 0,
yeah,
we know that Bn has to be big.
Yes.
And is it going to be kind of like previous Kn?
Yeah, actually, it's very much look like that. So it's an oscillating value here.
Okay.
That's sort of a property associated with sort of the fault.
Oh, I see. Yes.
So, try yourself, not bad.
Yeah, I'll take a look at the proof.
Yeah. And I have a little more computer series to look into.
So when GT is odd, AN is 0.
Yeah.
GT is even, BN is 0. Like,
yeah, that's right.
yeah?
You can see that, yes.
Okay.
Actually. Yeah.
Okay.
That's, and then there's a little assumption when G of t is a real, of course, usually we deal with the real function. Sometimes there's so-called complex.
Actually, oh, then it has to be different thing.
Yeah, it's a different approach.
Okay. Okay.
But yeah, that's your. But you know what? What I would suggest is, I suggest you can make a mistake. You can make. No problem at all. Yeah. Yeah. Just a second. Let me stop this.